Okay, I'd like to walk through example 4.1 in the book. This is talking about Motopower. I've got the example on the left. I've got table 4.2 below. I'd like to walk through calculating capacity improvement potential and percent capacity improvement potential using this information. I've copied this table into the Excel on the right. And here is a list of 20 part numbers. These are springs that go into gas-powered lawnmowers and snowplowers. This is the time study that was done. The first column of data here in column C is theoretical process time. The next column is supporting process time. We see here in row 7 there was some machine setup time. The paint was refilled. In row 9 there was a quality issue which necessitated some additional support process time. Row 13 there was 13 minutes while there was waiting for repair. So there's repair done to this part number. Row 19 there was a quality issue. This part was actually scrapped due to paint quality. And then the last support here in row 22 is a worker took a 3-minute break. The effective process time are these numbers here for each one of these. So how do we go about finding what the capacity improvement potential is? The capacity improvement potential is the gap between the theoretical and effective capacities of a resource. So if we're looking at this paint station as a resource, what is its theoretical capacity and what is its effective capacity? And the difference between those two is the capacity improvement potential. Conceptually, what that means is if there's a large difference between the theoretical and effective, there's going to be some potential to improve that effective time. If the difference between the effective capacity and the theoretical capacity is very small, then the potential for improvement is also going to be relatively small. So the first thing we want to do here is find out what is our theoretical capacity. And let's just do that here by looking at the average of our theoretical process times here. So I'm going to come up here, I'm going to calculate our average, and that looks like 2. Let me go ahead and put it into a couple of decimals. Sure enough. What does that mean? That means on average, the theoretical process time for each part is 2 minutes. But what we want to do is calculate our theoretical capacity. So how do we calculate our theoretical capacity of the resource if what we have is, on average, it takes 2 minutes to process one part? What we do there is we are going to calculate how much time it takes per spring. So we're going to take that 2, which in this case is the average, and we are going to calculate how much time does it take per spring to make that. So we're going to put this 2 minutes per spring. We're going to change this to how many hours per spring. And how do we do that? We simply calculate 2 divided by 60. So let's do 2 divided by 60, and that gives us the hours per spring. How much time it takes for each spring, but in terms of hours. And let me put this in 2 decimal places here. Okay, we want to make one more calculation, which is how many springs can we do per hour? This is the theoretical capacity number, which is measuring what's the capacity of the resource. So instead of measuring at a product by product level, instead of measuring how much time it takes to do one product, we want to figure out, and we want to take that 0.0333, and we want to use that to figure out how many springs we can do per hour. So we're just going to flip this around. And that's going to give us 30. What does that mean? That means we can paint 30 springs per hour on average. Okay, so now that we have our theoretical capacity, the next thing we need to figure out is our effective capacity. What is the effective capacity of this resource? And we'll do a very similar calculation here. We're going to calculate the average effective process time for these parts. Now what's interesting here is I could do the average formula just like we did before, and that would be 2.96. Interestingly enough, let's see, I'm just doing some centering here. This does not take into account the fact that from an effective capacity perspective, this part was scrapped. So M16 was scrapped. So instead of dividing by 20, I'm actually going to divide by 19. And that's going to give us a more accurate indication of what the effective capacity is. So I'm going to manually create this. I'm going to include the 2 minutes for that part, even though the part was scrapped. But I'm only going to include 19 because that's a better indicator of the actual or effective capacity. So let's see, I'm still trying to do some formatting on the number. Let's go to 2 decimal places. There's our average effective capacity, 3.2. So if we do some of the same calculations that we do over there, we come up with a springs per hour, an effective springs per hour of 19.26. So this is our effective capacity. 19.26 is our effective capacity, and this is our theoretical capacity, 30 springs per hour. Conceptually, what's the difference here? Theoretical is saying, well, if there's no downtime, there's no repair work, there's none of these other times where we have to fix something or wait for something, that this is the most springs we can do per hour in this resource, which is 30. However, the 19.26 takes into account the issues of refilling, of repairing, of waiting, of scrapping, of taking breaks for the resource, actually not the worker, right, just for the resource. That only produces 19.26 springs per hour. So now that we have the theoretical capacity and the effective capacity, we can calculate a capacity improvement potential. And what we're going to do is we're going to take our theoretical and we're going to subtract our effective. And that is a 10.74. What does that mean? That's actually a minutes, or excuse me, per hour. That's a per hour figure, which means there is potential there to improve, 10.74. Now the percent capacity improvement potential is a very similar number. We're going to take the difference and we're going to divide by the effective. So the percent difference is actually, in this case, a huge percent difference, almost 56% capacity improvement potential on a percentage basis. And that is how we can find out what kind of potential we have to improve the effective throughput.